All right, good morning. Can you hear me? Good morning. Today's topic is all about speed. So I will show you 3 different ways on how you can make Python programs more faster. And if you have time, I'll also show you how you can identify slow parts in your Python program, which is an essential aspect of speeding up your scripts. So the first thing of the speed up that we can obtain is by using NumPy. I've talked about NumPy the last lecture, and but today comes the part of NumPy that we can actually gain significant part of speed ups. So just by replacing your lists with NumPy arrays doesn't help to such a large extent, but by using so-called vectorization, you gain the actual speed up that you're looking for. And vectorization essentially means that you remove the loops. So the goal is always to try and remove for loops that you have in your program that are the slow parts. So if you're looping over a large amount of indices, these are the components that have the potential to be removed using vectorization. So okay, so the first thing that we need to learn in NumPy, if you have a NumPy array and you perform arithmetic operations on it, then these are applied element-wise. So if we have here we just have a linspace, linearly distributed numbers of arrays, and we multiply it by 3 and subtract -1. Then we get vector b out, and that b vector we can actually print. And you can see that this 3 times a minus 1 from import NumPy SNP. You can see that the output is also, so if here I print b, the output is also a vector of with 11 entries. But now instead of, we applied this 3 times a minus 1 on each element of a. Okay, and so this is called element-wise operation, but it's also called vectorization. So these operations here are applied to the entire vector, on each element in the vector. So if this was a normal Python list, what 3 times a would do is it would just triple the list instead of applying it vectorized. So here you see the difference between Python lists and NumPy vectors. And the same thing also happens if you use other NumPy operations. So for instance, if NumPy comes with a sinus function, so if you call np.sin, then you get the element-wise sinus function applied to the vector b. And the same thing with the exponential and so on and so forth. So there's many functions that mathematical functions that come with NumPy that you can use immediately and that are vectorized. So what is the advantage of writing it like this? We could also just create a loop where we loop over all the indices of a and compute the sinus or the exponential on each element. The answer is that doing these array operations is much, much faster than writing out the loop explicitly. So let's compare doing this element-wise operation versus a loop on an array that has 10 million entries. So here is the implementation where you loop over all the entries. So you have, I just create a new array of the same size with zeros. Then I loop over all the entries, and then I perform the computation element-wise. And if you time that, then you get a runtime of roughly 10 seconds. So now, if you do the same thing and you use the NumPy implementation, so first of all, you reduce your code to just 1 line, and it takes 0.1 second. So I can just demonstrate that. So if I start the program 1, 2, 3. Now it's running. So you see the star here means that the program is still running. And then when in about 10 seconds, hopefully. There we go. So now it finished. So that was this applying simply 3 times a minus 1 on 10 million operations, roughly 10 seconds. And then again, I do the same thing with NumPy in the vectorized version. You can see the star there was not even visible. It was immediately finished. Right, so here you can see the potential. I mean, this is now 100 times faster and significantly more elegant code. Yeah, roughly 70 times speed up. So, of course, sometimes you have functions where there is no immediate equivalent that NumPy provides. So the question is, can you also apply this vectorization to user-defined functions? And yes, it's possible. And I'll show you how that works. So imagine you have implemented a function called myfunc. It takes an x, and then it checks if f is larger than 0. In that case, it returns 0, and otherwise it returns the squared x. Okay, so fairly simple function. And now the idea is we create an array, and we want to call that function on with the array as an input. Okay, and so we are hoping that now the output would be that this function would be applied element-wise, right? But of course, if I don't do anything else, if I just try to run it like this, this doesn't work, and we can look at the error message. It fails here in line at this comparison, x is larger than 0. Okay, and the error message is something like the truth value of an array with more than one element is ambiguous. Okay, so let's try and understand what's going on. So we call myfunc with a NumPy array as an input. So this x here is going to be NumPy array. And then the first line here is if x is larger than 0. Okay, so on the left side, we now have a NumPy array, and on the right side, we have just an integer. And so the error message complained exactly about that. So it complained about the fact that you can't compare an array of numbers to a single number. It's not, some of them might be 0, some of them might be smaller than 0, some of them might be larger than 0. So this if statement is simply not well defined. Okay, so this is the error message that you're getting. And the problem is, of course, that's not what we want to do, right? We don't want to compare an entire array and check if it's larger than 0. We want to compare if for each element we want to check if it's larger than 0 or not. So this is not what we want to do. So we need to find another approach. So yeah, so the problem is that myfunc operates on the entire array instead of element-wise operations. Okay, so of course our immediate approach would be to write out an explicit loop and apply the function on each element. So again, I create an empty NumPy array of the same length as the original one. And then I created a loop here. So here's a trick if you have to write these loops. Here in this loop here, I need to loop over the elements of A, but I also need to have the index of that element, because I need to write into the ith in the associated index in the out element. And so there's this useful function np.nd enumerate that you can use in a loop, and that always returns a tuple. It returns the index and the value of the element itself at that index. And so then inside the loop, I can simply write out of I equals myfunc of ele. So I compute the value, I apply the element to the, apply the function to the element, and then write it into the same index in the out array. So of course we know loops are slow. Let's see how slow. Okay, so let's try and run it again. So it roughly takes maybe 2 seconds, or 1.3 seconds I've measured. So this is slow for, I think the array was 1 million long. So much better solution is to convert my function explicitly to a vectorized function. And so in NumPy, you can do that as follows. There's a function called np.vectorize. You give it a function, and it returns a new function. And that is the vectorized version. And so now, when you call that vectorized version of your function to a NumPy array, then this it applies the function element-wise. So we can do the same trick again. We run it, and yeah, it's let's see what I've measured: 0.3 seconds. So that's a lot faster. And just a comment here. So do you remember what these functions are called that take in functions and then return a modified version of the function? Yeah, it's a decorator. So instead of doing this step here, I could have also just decorated my original function. So just to demonstrate this to you, I could have also just, where was my, up here. If I wanted to fix that, I could just write add np.vectorize and see how it works. Right, so this is a more elegant way of, so now it works and it's fast. And this is more Pythonic because I just, yeah, this is more readable than the original version. Does it make sense? Okay, so much to vectorization. So the take-home message is, if you have a slow NumPy code, the way to improve it is to try to get rid of for loops. That should be a general strategy. So just to finish up with NumPy. So one important aspect of working with a large number of numbers is always to plot them, because you get a lot more understanding out of plots, usually, than just looking at the pure numbers. So plotting in Python is almost always done with a library called matplotlib. And I just want to give you a quick introduction on how to use matplotlib in practice and some best tips. So it's a huge library. It does loads and loads of different plottings. Sometimes it can be a bit overwhelming what it can do, and especially the syntax. So for simple plots, what I show you today, that's often very trivial. But as soon as you want to do more complex plots, then it can be a bit more complicated. And so what I do often is I go to this, there's a web page called the Matplotlib Gallery. It's a long website that shows you all kind of plots that have been created with Matplotlib, but it also comes with the source code of that, how that plot was created. So then what I often do is I just look through the plots and I find kind of a plot that I like, that looks as close as possible to the one that I want to have. Then I download the source code and I adapt it to my needs. So it's just my my recommendation for you to create pretty plots. But we start with a very simple plot. So let's say we have just a one-dimensional XY data that we would like to plot. And the way you do that is, well, first of all, you need to import the matplotlib library. And there's actually different interfaces on how you can create plots. I usually use the pyplot module to do the plotting. So I load up this pyplot module, and I typically call it PLT to have a shortcut. Okay, so then what you do, you create some X. So for one-dimensional graph, you need some data points on the X-axis, and then you need the associated data points on the Y-axis. So you create some X points with a linspace function. Then you apply a cost function on these X points and maybe an exponential function. And so the way you plot that is you simply write plt.plot X and Y. And you can repeat that in order to get multiple plots in your graph. Let's see how that looks like. There we go. So there we have our beautiful plot with the x squared and then the exponential going up. So of course, sometimes it's, so this is, I just want to tell you, so this is useful for your own sake, just so that you can inspect the data. But it's also really, really useful when you write your bachelor or master thesis and you want to visualize the data. And then, of course, when you publish your results, then it's also important that you adjust your plots a bit more. And so typically adjustments that you would like to do is change the line color, the thickness of the lines, the type, maybe add some additional labels to the plot. And of course, there's options that you can use to do that. So just to give you the most common options here is to add a label to each line. So here I call it, so this will show up in the legend, cos and exponential. You can specify the color of the line, how thick the line is. And then also here, the line style. So minus simply means a kind of one thick line, while then this becomes a dashed line if you have a double minus. And then you have some labels for the x and y axis, and then you specify that you want to have a legend also. So we can plot this. You can see this looks like a much more publishable figure already. And so one really useful function again is the savefig function that takes the plot and saves it as a PDF file, or you can also output it as a PNG file. And so you can load that immediately into your thesis afterwards. So typically what I do is when I write a paper, my simulation scripts, they output the results normally immediately as these, or they automatically generate these plots and store them in a separate directory. And then in my LaTeX files, where I write my paper in, that simply loads up these files that were generated. So I kind of have the entire pipeline generated, so that if I need to make changes in my code, it immediately gets reflected also in the paper or in the thesis. So then, of course, there's loads of other plots. Just to show you, if you want to have a scatter plot, let's just splint this one. So now I use pld.scatter instead of pld.plot. So here you get a scatter plot where the x and y. So a scatter plot means that you might have multiple values on the y-axis. And a normal plot is always, for each x value, you have exactly one y value. While a scatter plot is kind of distributed points equally in the x and y plane. So here what I used, I created some random numbers around 0 and 1, around 0, both for x and y. And then that's what you see here as a plot. With some nice coloring scheme. Okay. So the same thing is, of course, I've already shown this to you is, at the very beginning, but if you have a custom function that you need to plot, for instance, f of x, of course, the first thing that you need is to implement that function. Then you need to specify how many x points you want to use for the plotting. So the more points you choose in this lin space, the more accurate your plot becomes, so to speak. And then you evaluate that function for all these x points. So if your function is very expensive, you need to be careful that you don't choose a too fine x array here. But if it's a cheap function, then you can use quite a fine spacing. Oh yeah. And then you plot your function. So just a final tip. The default Matplotlib settings are actually quite ugly. So there's certainly not there's been a programmer who wrote the library, not a designer. So what I typically do is to, in order to get better or more prettier plots, is to use this library Seaborn. And essentially what it does is simply by importing Seaborn, it overwrites some of the style parameters in Matplotlib, and the resulting plots look a lot nicer. So it's a very simple trick, but it has quite satisfying results. So really the only thing that you need to change is add this import Seaborn statement here. And the resulting plots look much nicer. So I actually think the plots that you've seen before, I had called the Seaborn before, so I think the style difference might not be so obvious now, but you'll see it yourself if you create standard plots.
So it seems like you can modify your plot on the go, like you just, like when you write plot on the second line there, you just add another line. What's actually happening there? Since it's not creating a new plot, it's just adding to the last one.
Yeah, so you're asking, yeah, so your question is, how is it possible that, so if I wanted to have a third plot, I would just do this, right? So what's going on is that Matplotlib has kind of a default plot that it's called a figure, right? So when you call this plot function, it adds that specific plot to the current figure, to the working figure that you're working on. And then when you call it again, you add another line to that figure. And then you add another line to the figure. And then you add a label to that figure, and at the end, you actually show it. And so then there's also a reset function, where you say, now I want to clear my figure, and I actually want to start a new plot at that point. Yeah. So it's a good point. So you have to be aware that this is kind of, you're implicitly working on a global figure in Matplotlib. You can make it more explicit, but by default, this is how it works. Any more questions regarding plotting? No? Okay, then let's continue with, let's see. Okay. So the next part that I want to talk to you about is profiling. So the strategy now is I want to profiling is the task to identify slow parts of your program. And the reasoning why we do that is because if you're faced with a script that takes way too much time, and your task is to make it run fast. And it turns out that in almost all cases, the slow runtime of a code is caused by only 5% of the source code. So if your entire source code might be 1,000 lines, but actually the part of the code that causes the slowdown is only 5 to 10 lines of code. And profiling is the procedure to identify these 5 to 10 lines of code that you need to optimize. Because the rest you don't care about, right? So if your code takes 100 minutes to run, and 995 lines take 1 second, but there's then kind of these 5 to 10 lines where all the time is spent. And so you need to identify them before we can start optimizing them. And and so there's different ways on how you can identify these slow lines of code. And I want to show you 3. One is called timing, and then the second one is called profiling, and the last one is line-by-line profiling. So, but before you start trying to identify slow parts of your code and try to make it faster, the most important thing is always to actually get your code to work first. Right? There's no point optimizing your code if it doesn't produce the correct results yet. Right? Sorry, of course, first make it work. So that simply means it shouldn't crash. Right? That's kind of the minimal standard that you should be working with. Then make it correct. And then the last step should be to make it fast. So always keep that in mind before you start trying to speed up your code. Okay, and then in order to be able to optimize, we need to identify the slow parts of your code. And so profiling allows us to take certain parts of your code and measure it in terms of resources that are being used. And of course, time is a very common resource, how much time is spent in a specific part of the code, but it's not the only one. It could also be, for instance, how much memory is used in that piece of code, but it could even be maybe how much disk input-output is being used or how much network resources are being used. But for today, we focus only on the timing, on the resources in terms of time, so how much CPU time is being used. So generally speaking, if your task is to identify slow parts of the code, the simple techniques are often the most effective ones. So if you can, just start really, really simple and then switch to more complex techniques if needed. So specifically, if you're interested in CPU time, the simplest technique that you can apply is to do a manual timing. I'll show you in a second how to do that. Then if you want to be a bit more advanced, you can use the timeit module, which I'll also show you. And then finally, I'll show you the cProfile module. So as a case study, let's look at this, the task of filling up, applying a function to a grid. So we have a two-dimensional grid, and we want to evaluate a function on each of the grid cell. Now our implementation looks like follows. So this is the code that we would like to speed optimize using profiling. So how does it look like? We have a class that represents the grid. It takes in some the edge points of the grid, xmin and xmax, ymin and ymax, and then the distance from one point to the next. Okay, and so what do? I use the I store the all the x coordinates and all the y coordinates. I use arange to create numpy arrays for that. So I already use numpy array because I know pure Python lists would be too slow. And then I have the grid loop function. So this is the one that goes through all the grid points and applies the function to it. So then what do? I create a new array that will store the results. I just fill it with zeros. And then I loop over all the x coordinates and over all the y coordinates. And then I apply the function f, x, and y. So this is the x coordinate, y coordinate, and I store the result in the output array. And that's it. Okay? So let's see what's going on. Okay, so in order to use that, we first create a new grid. So let's actually run this so that I can. Okay. Let's create a new grid. And then computing the grid values, you need to specify the function that you want to have applied to. So for instance, sin is xy plus y. And then you can compute the function, and you can already see it takes quite a bit of time. So see, I mean, maybe 2 seconds or so. Okay, so the very simplest strategy to measuring your CPU time is simply measuring the clock time that's going on. And so the way you do that is you import the time module, and you measure the time before you start the code. Then you execute the code that you want to inspect. Then you measure the time again after the code has been executed, and then you simply print out the difference. And that's it. It's a really, really simple strategy, but very, very effective. So in our case study, we have two parts that could be potentially slow. The first part would be that the initialization of the grid takes a lot of time. And the second part could be that this calling g.grid loop is slow. So in order to dissect and identify the slow part, we need to do the timing for each of them separately. Okay? So then what do? I import the time module, and then I call the for loop. And then I do exactly the strategy that I just explained. So I initialize the grid here, and I add the time before and afterwards, and print out the difference. And because, so one thing that you should, again, a best practice here is when you do timings, first of all, your machine should never be busy with other things, right? So if you're compiling a program at the same time while you're doing timing, then then these timing results might be not correct. And so, but also maybe your operating system is decided to do some tidy up processing while you're doing your timings. So for that reason, it's always a good practice to perform the timings multiple times. Just perform the experiment multiple times and record the timings so that you can get an idea on what the actual time is that is being used to perform the code. And so this is what I've done here. So I've run the experiment 4 times, or 3 times, as you can see here. And yeah, you can see that the run times are roughly in the order. You can see that there's quite a bit difference, right? So first it took 4.2 to the minus 5 seconds. Then here it was actually 0.0029 seconds, and then it was again in the order of 10 to the power of minus 5 seconds. So you can see that there's quite a big variation from experiment to experiment, but it's all in the order of 0.-4 or 0.-5 seconds. And then we do exactly the same thing for the grid loop function. So again, I do 3 experiments, and now I time the grid loop function. So that's the only difference. And so if you run this, then we get these timings, and we can see that the grid loop function takes roughly 3. Again, you can see how much variation there is, but we're talking about in the order of 2.3 seconds, between 3 and 3.5 seconds. And so it's clearly the grid loop function that is the slow part in our program. It's not the initialization of the grid. Okay. Yeah.
Assignment, I used to time it. The difference between those, or
Time and time it.
yeah, I imported time.
Yeah.
Not time it.
Yeah. So time it I will explain in a second. So time is a module that gives you access to the current clock time and the date and so on. While right, and this is what I use here. So if and we should probably do that. So if you just do print time.time, let's see what we. Okay, so what this time.time function does is it returns the number of seconds since 1970, a specific date in 1970, I think. January 1st? Yeah, thanks. So, and this is the number that you see here, right? And so, of course, that's kind of that's not very meaningful. But if you call that function once before, once and then again, and you compute the difference, right? Then you get the number of seconds that was spent in the function here. And that's the strategy that we're using here. Yeah? So that's the time module. That gives you access to these kind of seconds information. But the time it module that's kind of it's a different module that is more targeted towards measuring the time that was spent in a specific piece of code. So I explained that now. Hopefully that answers your question. So so let's say you're not satisfied with this manual timing that I've shown you. So there's the time it module that makes this manual timing a little bit more convenient, and especially more convenient for small code snippets that you would like to time. And well, the way it works is as follows. You import the time it module, and then you call time it, then the statement that you're interested in timing. So in this case, it's just incrementing a plus equals 1. And then you also need to say what is kind of some setup values. So here I set a equals to 0. And then when you call this time it function, then it tells you how much time was spent on average in this statement here. So incrementing one number, incrementing a variable by 1 in Python takes roughly 0.06 seconds. And so, so by default, this command here is executed 1 million times, and it returns the accumulated runtime. So incrementing a number 1 million times in Python takes roughly 0.06 seconds. Okay? So you can, if you want to have the accumulated time not for 1 million times, but for 10,000 times, you can add this number argument here. And you can also repeat the experiment multiple times, as I've shown you before, that it's a good idea, by adding this repeat argument here. So yeah, this is a bit technical, but so if you have your own function that you would like to time, so for instance this g.quit loop, in this time it module need to it has its own namespace. So by default it will give you an error message saying I don't know what g.quit loop is. So then what you need to do is you need to import the quit loop in the setup routine. So then your setup routine would look something like this. From main import g in myfunc. And main in this case represents the main program. But otherwise it works the same way. So here the point is that instead of doing the manual timing, we could have also used this time it function or time it.repeat function to test our g.quit loop function. And you can see here that the timings roughly provide the same answers, right? It takes about 2.9, between 2.9 and 3.3 seconds for the g.quit loop. Okay, let me just see how we're doing this. Yeah. Maybe I'll, no, I showed this to you. I think it's quite cool. So of course the problem with what I've shown you before with these manual timings is that you already need to have a rough idea on where the time is spent in your program, right? But if you have 1 million lines of code and you have no idea, and you know that the program is slow, but you have no idea where roughly in the code it is going to be slow, then you would have to end up kind of randomly placing time functions, which would take a lot of time. So instead, you can use something called the profiling an entire program. And there's this module called cProfile that allows you to do that. So what it does is, when you run your program with cProfile, it automatically records how much time was spent in different functions, in all the different functions in your code. And then it reports it as a nice summary. So that will give you much, much quicker an idea on which functions are the slow ones in your code. So the way you run cProfile is you replace, instead of just calling Python and then the script name, you need to call it Python -m cProfile script.py. So what that does is it activates the profiler and it runs your Python program with the profiler activated. And while running it, it creates these statistics. Alternatively, you can also, so the first option here would profile the entire program that you're interested in. But if you're only interested in profiling one specific function, then you can also activate the profiling inside your code. And the way you do that is you first import the cProfile module. Then you create a new profile. So it's called cProfile.profile. And then you run the function of interest within that profiler. So in this, it's called pr.run, and then you provide the function that you would like to execute. And that executes the program, and then you get this results object, and this contains all the statistics about the runtimes. And then you can execute print stats to print out the statistics. And the results look like this. It's a bit overwhelming first, but I'll show you how to dig into it. So first of all, you can see that the first line tells you how long the overall runtime was, so about 2.9 seconds, which was the same as what we've seen before, right, for the grid loop function. And also that we had roughly, 1 million function calls. And so that somehow makes sense, right, because a little bit more than 1 million function calls. And that makes sense because our grid was 1,000 times 1,000 elements, and we called the function on each grid cell. So in total, we expect roughly 1 million function calls here. Okay, and then there's a long list of details, and I should maybe, oh yeah, so this becomes actually better if I zoom out. Okay, so the way you should read this is that you have here, maybe the most important thing here is first the last column here. This shows you the function that you're talking about. So each row here has the statistic for one specific function. So the first one is the grid loop function. You can see for the, I go from left to right. So per call means for each execution of that function, it took 2.9 seconds. And so grid loop was only called once, so it took 2.9 seconds. And then also, this is the cumulative time. So since it was only called once, it's also 3 seconds. And yeah, so I'm not actually sure about this. And this is the number of calls that it was being executed. So the next line is also interesting. The next one is the myfunc function. So this is the one that is being evaluated at each grid point. So that was extremely cheap. It's below the accuracy of the numbers here. So because it was just evaluating the sinus function for one number. But you can see that it was called 1 million times. And the total time spent in myfunc was 2.3 seconds. Okay? Oh yeah, and so now comes also this total time, that's also an important column. So that tells, we spent 3 seconds executing grid loop, but actually only 0.6 seconds was spent in grid, inside commands inside grid functions, while the rest was spent in other functions that was called from grid loop. So what I want to say here is that the grid loop mostly called other functions where most of the time was spent. And in that case, it was this my function. So the total time is split into my function executions, which is 2.3 seconds, and then other stuff in grid loop, which is 0.6 seconds. Does that make any sense? Yeah?
Does that mean that the actual double for loop takes 0.6 seconds to execute, but then for every time inside you call my function?
Yeah. Okay. Yeah. So, I mean, these 0.6 seconds, that include the for loops, and it also includes the initialization of the output array. Yeah. And then this guy here is all the sinus evaluations that we have, 1 million times. Yeah. So we learned quite a bit just out of that one graph. So just to, yeah, I guess I went through these already. So total time, yeah, so this is, total time is the total time spent in the given function, excluding time made in calls to subfunctions, right? So that was the point that I was trying to make. Yeah. Okay, but I think it's time for a break, and then afterwards, yeah, we'll dig deeper into this. Profiling 1.